Hey, good morning, everybody. Today we are moving into Unit 6, the integral. So I have good news for you. You are halfway through that first topic of calculus. We've talked about derivative, 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 derivative. We're going to take a little bit of a break from derivatives and talk about integrals. So what an integral does is it calculates area, and specifically area under the curve of a function from a point A to B. Now, I know that seems like a lot of information, but the way that I used to introduce this topic was start with geometry, that we have a triangle and you know the area formula is 1/2 base times height. And if you have a rectangle, you know that the area is base times height. And if you have a circle, we know that the area is pi r squared. If you have a parallelogram, the area is base times height. You might not remember these things, but you could look them up. If you have a square, the area is side squared. So for all these geometric figures, you have a formula. And you could actually get into octagons and pentagons and hexagons, and the area was 1/2 the apophthegm, if you remember that, times the perimeter. But what happens when you get a shape that looks like this? It doesn't look like any of these pictures that I did over here. And even when you get into that middle school math, you know, sometimes you'd take, whoops, jumped too far ahead. Sometimes you would take a rectangle and attach a triangle to it. You'd have these, you know, composite figures that you'd have to go through and find the area of and add them all up. But what I'm talking to you about today is this crazy figure that's underneath the curve above the x-axis between point A and point B. How do we find the area of that? And the answer is we break it into rectangles. So this is what's shown over here on the left. I have all of these rectangles, basically slice it up. And if I find the area of each individual rectangle, I can add them up and estimate the area under the curve. So I know it's not exact yet. We'll talk about that later. It's not exact, but it's an estimate. Like this one's too tall, this one's too short, too short, too short, too short, half and half, and then this one's too tall. So it's not perfect right now, but we'll work on that. So the way that we do this is we divide the region into even subintervals. Now I say that here because the AP exam likes to do uneven subintervals. So we'll keep that in mind later. But we call that our delta x, that's the width. So it's b minus a over n, where n is the number of rectangles. We construct a rectangle in each subinterval. So there are 3 ways to construct your rectangle subintervals. We have a left endpoint. We have the right endpoint. And then we have the midpoint. It's a little bit like Goldilocks. One is too short, one is too tall, one is just right. Truthfully, they're all estimates. None of them are perfectly perfect. But the area is the sum of the rectangles. I should say area of rectangles. It's the sum of the area of the rectangles. So you add up each individual one. A better approximation is found with many rectangles. In fact, if you had an infinite number of rectangles, that's better than the 4 rectangles that are shown here, or the, whatever this is, 6 rectangles, 7 rectangles that are shown up here. The more rectangles you have, the more accurate it is. So what does this look like for us? Compute each of the following areas for f of x equals x squared plus 1 on the interval from 1 to 3 using the method given. Now, I've graphed this for you already, and what we're looking to do, oh goodness, this keeps happening. We are looking to find the area between 1 and 3. 1 and 3, between 1 and 3, between 1 and 3. For the first rectangle, you're looking at R4. So these are 4 rectangles. And that R means right endpoints. So we have to divide the region between 1 and 3 into 4 rectangles. So here's 1, and I'm going to divide it in half. That's 2 rectangles, and divide it in half again. So there's 4 rectangles. Now, a right-hand rectangle means it's the right-hand side of the rectangle that hits the curve. So for this particular example, they are too tall. If it were a decreasing function, they would be too short. But for this one, they are too tall. So those are my 4 heights. Now we need a delta x. Remember, that's b minus a over n. So it's 3 minus 1 over 4. 3 minus 1 is 2. Over 4 is 1/2. Okay. So for right-hand rectangles, it is going to be your delta x times f of 1.5 plus f of 2 plus f of 2.5 plus f of 3. So I have my 4 rectangles, and I'm going to evaluate them at those x values. I'm going to evaluate the function at those x values. Why did I start at 1.5 and not 1? Because I'm looking at the right-hand side of the rectangle. I'm over here at 1.5. So I'm going to put 1.5, 2, 2.5, and 3 into my function, the x squared plus 1. So here's my 1/2. I'm going to cheat with a calculator. So 1.5 squared plus 1 is 3.25. 2 squared is 4 plus 1 is 5. 2.5 squared plus 1 is 7.25. And 3 squared is 9 plus 1 is 10. Okay, so I'm going to add all of these up. Divide by 2, and I have 12.75. You don't have to worry about units. I know we're talking about area. In middle school, they hound you to death with units, but you don't need them. So the estimated area underneath the curve is 12.75. So we're going to try it again with the next example. This time we have L4. So instead of being right-hand rectangles, these are going to be left-hand rectangles, and we still have 4 of them. This time, if I draw left-hand rectangles, it's the left-hand corner of each rectangle that hits the curve. So now my rectangles are too short. This one's going to be an underestimate on my increasing function. If it were decreasing, they would be too tall. So we've got 4 rectangles. They are left-hand rectangles. My delta x is going to be exactly the same. It's 3 minus 1 over 4. It's still 1/2. In fact, this is going to look very similar to the right-hand rectangles. But instead of starting at 1.5, we need the x value for the left-hand side, which is 1. So f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. 1, 2, 3, 4. If you notice, we didn't use the 3, and that's okay. Students get a little happy listing them all out, and sometimes if they're not careful, we'll wind up with 5 rectangles over here, but remember, we only have 4, so don't list that f of 3. So we have a width of 1/2, f of 1, if I put that into the original function up here. 1 squared is 1 plus 1 is 2. And then I'm going to cheat and use the values that I already figured out on the left-hand side there in red. And I don't need the 10 because we didn't use f of 3. So when I add these up, I've got 2 plus 3.25 plus 5 plus 7.25 divided by 2 is 8.75. So not surprising that it's less than our right-hand rectangle estimate. I did expect it to be an underestimate. So one's too tall, one's too short. Let's talk about a midpoint. Midpoint maybe is just right. So my midpoint, we're going to have 4 again. This time it's the middle. This is a little tougher to draw. It's the middle that determines the height. So the middle of each rectangle determines the height. That's probably the middle. So they go a little bit over and a little bit under at the same time. I'm not going to show you delta x again. That's exactly the same. So midpoint for 4 rectangles is going to be 1/2. This time when we do our f values, it's not 1 and it's not 1.5. It's directly in between. It's 1.25. And then it's not 1.5 or 2, but it's 1.75. It's exactly in the middle. Plus f of 2.25 plus f of 2.75. So we're going to put all of these decimal values into our function. I'm a little bit out of space here, 1.25 squared plus 1. Now, don't forget at least 3 decimal places. I've seen some of us rounding a little bit too much. 4.063 plus, whoops, 2.25 squared plus 1, 6.063, and 2.75 squared plus 1. You guys can be doing this along with me. 8.563. Okay, so if we add all these up, I have 10 and multiply by 1/2 as well, 10.625, which makes sense. It's between the 8 and the 12, and that is, again, an estimate of the area. Now, it is entirely possible, and we will get there, but we're not there yet, to figure out what the actual area is. There's a couple ways to do it, but again, we're not there yet. That's the fun part. We got to lead up to it. 1, 3. The actual area is 10.6 repeating, 10 2/3. So this one's pretty close for the midpoint, So there we go. My trapezoidal approximation method. Now, if my rectangles weren't that great, we can do trapezoids. Don't forget that the area of a trapezoid is 1/2 the height, base 1 plus base 2. The height of our trapezoids will always be the change in the x, so they're sideways trapezoids. They go like this. I'm going to break this into 2 trapezoids, but this is what they look like. This is base 1, this is base 2, and then this is your height going sideways. That's your height. The y values will be used for base 1 and base 2. So for example 2, use a trapezoidal approximation to find the area using 2 subintervals. So we're going between 1 and 3 again. I think this is actually referred to Simpson's rule as well, I think. So here are my trapezoids, here are my trapezoids. Remember, this is my height, this is my height. We have equal heights here. Instead of pulling out that delta x, I'm going to do this as 2 separate trapezoids. So my overall area is going to be 1/2 height, base 1 plus base 2. And then my second trapezoid is going to be 1/2 height. This time I'm going to call it base 2 plus base 3. Sorry, I got tongue-tied. So here is base 1, base 2, base 3. So my height, how wide is each one? Remember, this is our height going this way. My height is 1. Base 1 is this y value here. So this is going to be f of 1. Base 2 is f of 2. 1/2 that height again is really the width between the slices. It's my trapezoid on its side. And this is going to be f2 plus f3. So 1/2, 1. F of 1, 1 squared is 1. This is 2. F of 2, 2 squared is 4. This is 5 plus 1/2 times 1. This is 5, and 3 is going to be 10. So what do we have? We've got 7 over 2 plus 15 over 2, which is 22 over 2, which is 11. So fairly close to that midpoint value. And when I told you the exact area under the curve was 10.6 repeating, a trapezoid is more accurate than a left or right hand approximation. So that's how we calculate Riemann sums. They are the basis for what we're doing next. Given a table of values, this is what they look like on the AP exam so often. If you were taking the AB exam, I would almost guarantee you'd see one in the multiple choice and very likely the free response. BC, you're still probably going to see one somewhere. The rate at which the water is being pumped into a tank is given by the continuous and increasing function R of t. A table of selected values of R of t for the time interval from 0 to 13 minutes is given below, using right Riemann sums with 4 subintervals to approximate the area under the curve. So this is the width. So here's 1 rectangle, here's 2 rectangles, here's 3 rectangles, here's 4 rectangles. So they have to give you 5 values in the table in order to have 4 rectangles. If we're using a right Riemann sum, we're using the right-hand values of each rectangle. I'm a visual learner, so I need to draw those in there. So we're going to have 4. So the area of a rectangle is width times height, base times height. So the first rectangle is 4 units wide and 13 units tall. The second rectangle is 2 units wide and 18 units tall. You see where this is going? The third rectangle, it's from here to here, is 4 units wide because 10 minus 6 is 4, and 23 units tall. And the fourth rectangle is 3 units wide and 27 units tall. So they didn't give me a function this time, and they also have different widths for the intervals. And that's what happens on the AP exam. They almost always have different widths like that in the table. 2 times 18 plus 4 times 23 plus 3 is 27 is 261. Now, what does this represent? So the rate at which water is being pumped into the tank is given in gallons per minute, and we've talked about minutes. So what does this represent? This is 261 gallons of water pumped in from 0 to 13 minutes. So that's how much water we've calculated, how much water went in. The area under the curve is how much water. Is the approximation greater or less than the true value? We know that it's increasing, so we know it's going uphill, and we used right Riemann sums. So think about that picture that we had on the first page. Increasing right Riemann sums. So this is an overestimate, so this is greater than the true value. I can't write this morning. Greater than true value. Okay. Excellent. Example 4, I think this is the last one we have. The rate at which customers are being served at starbursts is given by the continuous rate function R of t. A table of selected values is given below. At t equals 0, there had been 200 customers served. Use a trapezoidal sum with 4 subintervals to approximate how many customers were served after 10 hours. So we have the rate. So my first trapezoid is 2 units wide, which remembers my height. So I've got 1/2 times 2, base 1 and base 2, 37 plus 44. And again, these have different widths, so we have to treat them as separate ones. 1/2, my next width is 1. My 2 bases are 44 plus 36, plus 1/2. The next width is 3, 36 plus 42. My next trapezoid is a width of 4, and 42 plus 48. All right, there we go. There's our area. 37 plus 44 is 81. This is going to wind up to be, this one is 44 plus 36 divided by 2. This is 40. This is 36 plus 42 times 3 divided by 2 is 117. Whoops. Man, oh man, that's happening a lot today. This one is 42 plus 48. 180. So now if I add all of these together, 117 plus 40 plus 81 is 418. Customers between 0 and 10 hours. But don't forget, at time equals 0, there were 200. So we have to take that initial amount, 200 plus 418, and we get 618 customers served. There you go. Riemann sums. A lot of word problems, a lot of multiplying, a lot of adding. So this is the basis for what comes next. Let me know if you've got questions.